Skyscrapers are becoming more and more elegant and unique in their designs. In fact, over the past few decades, there has been a major push to make new skyscrapers as exotic as possible to put it on the map as a landmark for everyone to remember. For example, that big fish-shaped building in Dubai, which I don't know the name of, and I don't actually know if it's in Dubai either. So maybe the idea of making a building unique enough for people to remember doesn't always work out. But it doesn't stop people from trying, and it's that trying that can create major aerodynamic problems for these buildings. For example, in Figure 8, we see a really cool shaped building, and in fact, the keen aerodynamicists out there would immediately understand the benefits of twisting this building for its aerodynamics. Here it would severely reduce the loading that a oncoming street would place on it because the vortices would shed along the sharp edge, and because that sharp edge isn't straight but actually rolls around the building, the loads on the building would be more axisymmetric. And I also didn't know that this building even existed before seeing this paper right now. So I guess this is another example showing how the marketing principle of making a building unique may not work all the time. But anyway, this building is a little unique in that its shape has some beneficial aerodynamic properties. That is not always the case, and in fact, it's actually rarely the case. So how does making a building more aerodynamic, how can you do that? And I guess why would you want to do that? Well, to answer the second question, we can think about the increased loading on the building, which means that you need to use more materials to make the building strong enough to withstand the additional loads. What's more, it could even produce noise which is unpleasant. And to answer the first question of how you can make a building more aerodynamic, we are looking at this paper called Computational Aerodynamic Optimization of Wind-Sensitive Irregular Tall Buildings. So the authors of this paper had a dream, and that was to develop a CFD and FEA model that can reduce the loadings on a building, and in particular an exotic building, without changing the facade too much. Did they succeed? Let's find out. This paper, by the way, you can find in the link below. So as mentioned, these researchers had to couple CFD with FEA to make what is called an Fluid Structure Interaction Model, or FSI for short. And as soon as you do that, the time it takes to simulate your CFD skyrockets. That is because you have to share so much data between the two halves of the simulation. So first of all, you might do the CFD side and then get the aerodynamic numbers. Then you feed that into the FEA side. From there, you then have to run the FEA, get the structural numbers on how the object has changed shape, and in this case, the building. Then you have to input that back into the CFD. Then you might need to do some kind of remeshing there, or even dynamic morphing of the mesh, and then run the next iteration of the CFD, and then so on you go. So there are a lot of steps, and anytime you have to modify the mesh, you're going to be there for a while. So as a side note, FEA is so much easier than CFD. To give you an example of industry standards, so let's say you have a project and you need to run CFD on it. You might need to use 100 million cells and run it on 500 cores. That might take 2 days or so. For FEA, on the other hand, you might only need 200,000 cells, and you can run that on a regular desktop computer for an hour and get your answers. That is the difference in the computational power you need between the CFD and FEA. So for their CFD, these researchers used an industry standard building, which is by the body called CARC, designed back in the 60s. So this CARC building is seen in Figure 2 here, and it's really just a normal rectangular building. The good thing is that they used wind tunnel results on this CARC building to validate their CFD. This building was tested in an atmospheric wind tunnel, which is good because, believe it or not, but buildings and us live in a boundary layer, and the turbulence density is high in this boundary layer, and if you were to use a wind tunnel for airplanes, then the flow conditions would be very different. So this is good attention to detail here. Now, something that is a bit ambiguous is that they say that a minimum blockage ratio of 5% should be met during the CFD to match the wind tunnel. Now, I think they mean that the blockage ratio should be below 5%. The reason for that is the higher the blockage ratio, the more the walls of the wind tunnel and the CFD domain will affect the results. And I'm not sure if the wind tunnel had an open test section or a closed one, but if it was closed, then even 5% is too high. It should be more like about 3%. If the test section was open, then 5% is pretty good. That's fine. One major flaw of this research is that they use the RANs, and that doesn't really give transient flow features, and buildings are bluff bodies, so transient flow features are very important. RANs just averages it all out. But I can understand why they went for RANs. With this fluid structure interaction, anything to reduce the computational time would be needed. However, there's also the issue of the equipment that they use to do the CFD. So they say that they used pretty much a regular computer. It had 6 cores, which could be hyper-threaded to make 12 virtual cores. It had 32 gigs of RAM, so the computational power was severely lacking for their original dream was. I think this is really a case of trying to do too much with too little. Anyway, I guess this is still a good proof of concept idea for this research campaign. So they tested 3 different turbulence models, the K-epsilon, the RNG K-epsilon, and the realizable K-epsilon. It's great that they tested different ones, but they are all very similar. They didn't test any turbulence models that were significantly different. It's kind of like saying you're going to test 3 different soft drinks, and those are going to be Coke, Diet Coke, and Coke Zero. They're pretty much the same thing. Like no one is testing Fanta. And that is really what's happening here with this K-epsilon family. It's because since its inception, it has been slated as the turbulence model that you use when dealing with bluff bodies. Now, back 30 years ago or so, when it was made, that was definitely the case. But times have changed, and the K-epsilon turbulence model is outdated and not really good for much by itself, compared to newer turbulence models at least. And figure 3 and 4, they kind of show this. So here are figures, let me zoom out a little bit here. Okay, here we go. So they all give pretty similar trends in terms of the reference value, which is the wind tunnel, compared to the different K-epsilon turbulence models. And I should mention that this plot is for the pressure tappings around the building. So anyway, they all give pretty similar trends, but there are some noticeable differences. And for 20 or 30 years ago, getting results this close with the CFD was everyone's hope. But now, with differences of like 10 and 20%, everyone shuns it. But in general, the RNG K-epsilon turbulence model here produced the best results compared to the wind tunnel tests, so the researchers went with that one. Now, in figure 5, we see their mesh, and they have an interesting mesh refinement set up here. Let me zoom in a little bit. So they have refinement zones in the projected directions from the building, but the wake doesn't seem to have a large refinement zone itself. That is a little unusual to me because the wake will be quite large because the building is a bluff body. And the width of the refinement zone downstream, I don't think there is really much of it there, and it should really be wider than the width of the building itself because the wake will be wider. So we'll have to see how that affects the aerodynamics of the building. Now the blockage ratio was only 1.05%, which is really good. I'm not sure if that matched the wind tunnel again, but at least for the CFD, that is a pretty decent sized domain. Now in table 2, we see their mesh. Let me zoom in a little bit here. Okay. So we see their mesh independent study, and they did a pretty good job in that they increased the number of cells they used for each refinement by quite a lot. However, the overall number of cells they used for the finest case was only 500,000, which is not exactly a lot for this kind of simulation. With this few cells, it would be hard to have a fine boundary layer mesh, and I can't actually find anything about their boundary layer mesh here. So I guess perhaps that is why they went with the RNG K-epsilon turbulence model as well, because they could use a coarser boundary layer mesh and still get somewhat decent results. Anyway, in figure 6, we see the results of the mesh dependent study, and overall, there was very little difference between the 3 meshes. They were all around about 12.5% off the validation data. However, the authors decided to go for the medium mesh because it did deliver slightly more similar results, at least, to the fine mesh than the coarse mesh, and this was with about a 25% reduction in computational time. So they weighed up the time to accuracy trade-off and went with the medium mesh. So overall, there were quite a few things that could have been improved upon for this mesh, and figure 6 shows that overall, the CT might be accurate to about 15% compared to the wind tunnel results. As such, I think from here, differences over 15% should be trustworthy. Differences below that should be used as just general indications and not necessarily correct. Now, to test their proposed FSI method to make buildings more accurate and more aerodynamic, they decided to use the Kayan Tower in Dubai, as shown in figure 8 here, as the case study. Now, apparently it is 306 meters tall, and that makes it the tallest twisting building in the world. And while the researchers wanted to see if they could modify the building to reduce the loadings, they still wanted to preserve the general shape of it. So they chose 2 fairly minor variables to modify. Those were the corner rounding and the building plan. So we can see these 2 variables in action in figure 9 here, where the corners could be rounded anywhere from a very sharp to a radius of 2 meters. The building plan is a little unusual though, in that it is a hexagon, I guess, but one side is flexed in instead of each side being flexed out, as you would have with a regular hexagon. And the angle in which it is flexed in is what the researchers altered, so they went from 0 degrees to 10 degrees. Now, one major step to this overall process was a design of experiments, which we can see in figure 11 if we scroll down here. So the blue dots are the building configurations they tested with the different curvatures for the degrees and the different edge radii. They ranged from almost no flex angle to 10-degree flex angles, and almost no to almost completely sharp corners to almost 2-meter radii. They selected these points through something called a Ladin hypercube sampling approach. Now, this Ladin hypercube approach ensures a random distribution, but it also makes sure that no two points are close to each other. That way you get a random distribution, but you also get a more uniform distribution too. It's a pretty smart way to make sure that you're considering every combination, and one pocket doesn't really get missed out on, which can happen if you just go for a very completely random and not Ladin hypercube approach. Let's now move on to the results because the authors do a great job presenting them. So in figure 18, if we scroll all the way down here, we see a 3D contour plot. Here we go. So on the left axis, we see the corner rounding radius, and on the right axis, we have the hexagon angle. And on the vertical axis, we have the deflection of the building, which is in millimeters. And this is experienced because of the other two variables here. So immediately it becomes clear that a smaller corner radius results in a lot more deflection, and a greater angle to the hexagon corner also results in more deflection. Unfortunately, the authors don't go into the flow physics as to why this happens, and I would have been really interested to see why, but that's how it is. So another thing this figure shows us is that there seems to be some kind of nonlinearity with these two values. For example, for the corner rounding radius, when it is pretty much sharp, so there's a 0 point here, and there is no hexagon flex angle, so the angle is 0 here, the building will flex up to about 305 millimeters. Then if you round the corners up to 1 meter, so about here, which is about half the maximum they tested, the deflection only drops to about 300 millimeters, so 5 millimeter deflection. But then, when you round the corners even more to 2 meters, the deflection drops to about 290 millimeters. So it seems like there's this massive nonlinearity whereby the more you round the corners, the less and less deflection results. Now, from a fluid mechanics point of view, that relationship will only hold up to a certain point, because once you start rounding the corners too much, then the building will start to become more cylindrical, and then the deflection will jump up again because the twisted edges, which breaks up the coherency of the vortex shedding, that won't exist anymore, and you'll get the vortices now shedding together and creating even more loading. So while this plot shows that rounding the corners is beneficial, what it doesn't show us is that there is a sweet spot, where exceeding that will result in tears for everyone involved. Now, the hexagon angle is a little more complicated because we see that at about a 5-degree flex angle, so about here or so, changing the angle either way dramatically changes how much the building flexes. Then it kind of stabilizes. Again, the flow physics behind this isn't discussed, and that would have been really interesting to see. But I guess what I would maybe say is that it probably has to do something to do with maybe the vortices shed from one side merging with the vortices from the other side with this angle, or perhaps the angle of 5 degrees gave the vortices that shed in this region to kind of hide in there momentarily, which would then increase the effects on the building. Those are just some thoughts that I had perhaps about the flow physics that's going on from these results. I'm not sure if that is the case or not. Now, this figure also shows us that the corner radius and the hexagon angle has this synergistic effect, because this plot is definitely not consistent. For example, let's take where the corner radius is 0, so about here, going from 0 degrees to 2 degrees, so here to here, there's actually a reduction in the deflection. Then going from 10 degrees here, you'll get a massive increase in deflection. On the other hand, for a 2 meter corner radius here, increasing the angle from 0 degrees to 2 degrees gives a slight drop in deflection, but not nearly as much as from the 0 meter radius here. Then increasing the angle from 10 degrees results in a much larger deflection too. So we can conclude that the general trends stay the same, but the magnitudes are very different, and that tells us that there are some synergistic effects. Overall, the optimal design is obviously where this dark blue region is, which corresponds to a corner radius of about 2 meters and a hexagon angle of about 4 degrees. So in figure 20, we see the improvements in the deflection from the original building for the optimal design. And there seems to be a consistent reduction of about 15% or so, which is really good. Another thing these plots show is that the higher up you go in the building, the more the building deflects. For example, on the first floor, there is pretty much no deflection, but on the 37th floor for this y direction, let's go here we go. So about here, there is a 100 millimeter deflection. Then for the 75th floor, there is now a 250 millimeter deflection. So that's pretty cool how there is this nonlinearity to the deflection. Now, these plots show that there is more deflection in the y direction than the x direction. The only problem is that I can't seem to figure out which direction is which for the building. I think that in figure 19, the y direction is the direction connecting the two flexed faces, so going like across the page. And then that means the x direction is the direction connecting the two flat faces, so going vertically across the page. But I'm not completely sure. I think that's the case. And if that is the case, then that makes sense because simply from a structural point of view, where the second moment of inertia here is greater for the x direction than the y direction. So that just means that the x direction is stiffer. Now in figure 22, we see the building loadings, and as you go up the buildings, you see how they change. It's really cool. Now, one trend to note is that for at least the x direction, so the right figure here, there seems to be two local maxima, and we've seen this in other podcasts as well, where at the top of the building, there is a local maximum here of over 150 kilonewtons, which isn't that much anyway. I mean, that's how much I usually lift in the gym, so no big deal. But we also get another local maximum at around 20 to 30% of the building upwards. And below there seems to be a boundary layer effect happening. But anyway, the take-home message here is that the optimal design reduced the loading by a consistent 20% in both the x and y directions, really. In some cases, it was even higher than that. And with that, we come to the end of this podcast. We can conclude that generally talking, the sharp edges of the building will always seem to be good if you start to round them just a little bit. And that these various features definitely work together to produce some synergistic effects. So if you like this podcast, make sure to hit the like and subscribe buttons. And if you want to learn how to do CFD, then take our course in the link below. And if you want to learn how to do OpenFrame, which is a really powerful and free CFD software, but hard to learn, then take our courses in the link below as well. And finally, if you're doing experiments, did you know that you probably have a 2 to 4% error in your data, but you didn't even know about it? In the atmosphere Hawk link below, I can't talk today, we go through why and how to fix it. So see you next one. Peace amigos.